Assalamualaikum warahmatullahi wabarakatuh and very good day. My name is Muhammad Aludin bin Muhammad Zulfakri, student ID MA24002 from the Faculty of Mechanical and Automotive Engineering Technology at UMPSA. Today, I'm going to present about process optimization using DMAIC methodology. Okay, so first, what exactly is Six Sigma? So at its core, it is a highly structured data-driven methodology designed to improve processes by identifying and reducing variation and eliminating defects. The ultimate goal of Six Sigma is to achieve near perfection, which statistically translates to no more than 3.4 defects per million opportunities. So originally developed by Motorola in the 1980s and later popularized by the global companies like General Electric, its core focus remains unchanged, maximizing quality improvement, operational efficiency, and also overall customer satisfaction. So next, why does Six Sigma matter so much in industry? There are four key drivers. First, it delivers high quality by ensuring fewer defects and higher product reliability. Second, it dramatically reduces costs to minimize waste and optimize resource utilization. Third, it boosts customer satisfaction because product and service performance becomes highly consistent. And finally, it supports continuous improvement, aligning perfectly with lean and Kaizen frameworks to foster an ongoing culture of efficiency. While Six Sigma started on the factory floor, its application spans across multiple domains today, including manufacturing, healthcare, and information technology. For us as engineers, it serves as an essential framework to help design, evaluate, and optimize highly efficient and sustainable systems, ensuring that operational failures are minimized before they ever impact the end user. So, the heart of the Six Sigma strategy relies on a structured five-phase roadmap known as the DMAIC cycle. DMAIC stands for Define, Measure, Analyze, Improve, and Control. By leveraging statistical tools and cross-functional teamwork, this cycle systematically hunts down process variation and eliminates root causes, yielding measurable results, lower operational costs, and superior quality. Okay, so next, let's take a macro look at the blueprint. In Define, we clearly state the problem and customer requirements to establish our project charter. In Measure, we gather reliable baseline data to quantify the exact scale of the issue. In Analyze, we use the data to isolate and validate the true root causes. In Improve, we brainstorm, test, and implement targeted solutions. And in Control, we standardize the new process to sustain our hard-earned gains. The core benefits are simple. It gives us a structured roadmap, enforces data-driven decisions rather than guesswork, and directly drives up productivity and efficiency. Next, let's break down how we apply each phase in our project, starting with the define phase. The main objective of the define phase is alignment. We must clarify the problem statement, identify specific project goals, establish clear boundaries on what is in or out of scope, and align all of these targets directly with customer expectations, often called the voice of the customer or VOC. To contextualize this, our project tackles a specific industrial problem, a high defect rate in frozen food packaging sales. This problem directly harms business performance to added costs and lower customer satisfaction. To address it, we establish a SMART goal, specifically to reduce packaging defects by 30% within a 6 month time frame, ensuring our engineer targets strictly support the company's broader operational strategy. To map out our territory, we constructed a SIPOC diagram. Our suppliers include local poultry farms, vegetable growers, and packaging vendors, while inputs consist of raw ingredients, packaging films, utilities, and labor. The process flows through eight key steps from receiving raw materials, cold room storage, preparation, cooking, freezing, all the way to packaging, sealing, labeling, and shipping. The final outputs are the frozen, ready to eat meals alongside waste logs, which go directly to our customers, including major retailers, distributors, and household and consumers. With the process clearly mapped out, we move into the measure phase to gather our facts. So, the purpose here is to establish an accurate performance baseline, collect highly reliable data, identify our critical to quality or CTQ metrics, and conduct a measurement system analysis or MSA to guarantee our data collection tools are completely accurate and free of bias. So we carried this out in three precise steps. First, we gathered current performance data using check sheets and production logs, ensuring a representative sample size. Second, we track critical quality indicators like defect per unit DPU and process capable indices like CP and CPK. Third, we validated our measurement system using gauge, repeatability, and reproducibility studies to completely eliminate operator inspection bias. So in this phase, some of the tools are used including Pareto chart, which shows most frequent defect types, and also SPC charts, which monitor variation over time. So next, tools like histogram and check sheets are also used in projects, where histogram displays distribution of process data, and check sheets are used because it is a simple data collection tool. Now that we have quantified the problem, we enter the analysis phase to figure out the why. So, the absolute goal of the analysis phase is to dig past the surface symptoms, identify the true root causes of variation, use data to validate our hypothesis, and prioritize the causes that hold the heaviest impact on our packaging line. To ensure no stone was left unturned, we utilize a fishbone or Ishikawa diagram. This structural tool prompts us to brainstorm potential failure causes across five classic categories, which are machine, method, material, manpower, and environmental. So here is my actual project fishbone for my projects. This is one of the examples of Ishikawa diagram. So we prioritize them by applying the Pareto principle, which focus on the vital few. For instance, data analysis revealed that variables like sealing jaw temperature and packaging film thickness accounted for a massive 80% of our total sealing defects. We feed these insights directly into a cause and effect matrix. So this is our actual cause and effect matrix. We systematically scored our process inputs against critical customer outputs. Using a mathematical top quartile approach where our maximum score is 108 and our selection range is bounded between 81 and 108, we mathematically isolated our key process input variables. In this specific life cycle phase, raw meat and vegetable quality scored a maximum of 108, securing rank number one as our primary input focus. Next, we advance our risk assessment using an FMEA, failure mode and an effect analysis. The FMEA approach calculates a risk priority number or RPN by multiplying three critical scores: severity, how serious the failure impact is; occurrence, how frequent it happens; and detection, how easily our current controls catch it. Any factor yielding a high RPN is immediately prioritized for engineering corrective action. So, looking at our operational FMEA table, we identified that all packaging machines causing seal misalignment carry an initial critical RPN of 224, while still lower ingredients from a lack of FIFO tracking score an RPN of 180. Thanks to our recommended actions, which included replacing key sealing mechanisms, installing auto calibration sensors, and implementing a digital inventory system, we successfully drove those high RPN risks down to completely safe levels such as 64 and 28 respectively. With our root causes fully validated and prioritized, we advance to the improve phase to execute solutions. The purpose of this phase is to develop thoroughly test targeted solutions that eliminate root causes. We focus on optimizing the process parameters for maximum efficiency, validating our engineering modifications using small scale pilot runs, and ensuring that every solution is highly practical and sustainable for long term operations. Our improvement and execution follow a three-step flow. First, we generated innovative ideas through cross-functional brainstorming, learning heavily on lean tools and Polka yoke error proofing, such as installing digital temperature sensors. Second, we piloted these changes on a small scale. Our pilot data showed immediate success with the defect rate dropping from 8% down to 4%. Third, we roll out the validate changes across the entire production line, permanently updating our SOP, standard operating procedures, and train our operators. Okay, so this is a Kaizen cycle from my project. As an example, we took a baseline data of 3.5% defect rate and 8% cold storage spoilage and set aggressive continuous improvement goals, which is cutting defects under 0.8% and spoilage down to 4.5%. We brainstorm layouts to enforce first in, first out FIFO, tracking, ran frontline workshops, track weekly performance metrics, and successfully standardized these upgraded production workflows. So, a key element of our improvement strategy was error-proofing or Pokayok. As shown in this engineering logic map, this is from our project, my project. So, we identified critical solutions like FIFO violations and seal failures. Instead of relying on human memory, we built physical and digital devices directly into the line, such as automatic packaging line halts during seal errors, barcode track auto calibration systems, and automated cold room alarms. This physically prevents defects from moving down the stream. The final and arguably most important phase of any project is the control phase. So, the core purpose here is sustainability. We must maintain the process improvements we achieve, continuously monitor ongoing line performance, fully embed our new practices into formal standard operating procedures, and firmly prevent the process from ever regressing into old and inefficient habits. We achieve robust control via three distinct mechanisms. First, statistical process control, where using control charts to constantly track our weekly defect rates and detect early signs of process drift before a defect is even created. Second, clear standard operating procedures, where we create highly visual checklists at every workstation so operators and supervisors know exactly what to audit daily. Third, sustaining the culture, where scheduling monthly Kaizen reviews and keeping performance metrics completely transparent to maintain accountability across all shifts. So next, let's look at this SPC chart, which is from my project. So this post improvement control chart visually proves our success on projects. Look at the dramatic shift after sample 5. By implementing our engineering controls, the seed defect rate plummeted sharply and stabilized beautifully under our tight new central limit of 1.348%, remaining perfectly bounded within our upper and lower control limits. This is a statistical proof of a stable optimized process. So, to anchor these gains permanently, we institutionalize this official standard operating procedure for our frozen food production line. It explicitly documents the step-by-step procedures for seal alignment calibration, automated barcode FIFA scanning, and mandatory cold storage temperature checks. It assigns clear responsibilities across operators, supervisors, and maintenance teams, ensuring our new baseline is locked in. So, after completing all the phases, let's move to our conclusion. In a nutshell, let's synthesize our entire DMAIC journey. To define, we establish our targeted smart boundaries. In measure, we gathered baseline defect data using gauge R&R. In analyze, we isolated root causes using Ishikawa and FMEA scoring based on our mathematical formula RPN equals to S times O times D. In improve, we executed error-proving Yopoka-Yoke and Kaizen pilots. And finally, in control, we standardized our procedures to lock in a true Six Sigma quality level, maximizing our process yield to an outstanding 99.9%. If we can follow all of these steps, we can eliminate variation and deliver near perfect industrial outcomes in all of any upcoming projects. Thank you so much for watching this video, and I hope to see you later.